which can be used to determine the crystal structure of any material. And those techniques mainly employ this Bragg's law, or what I would say the property of a crystal by virtue of which diffraction pattern is observed. So most of the times we actually are looking at a diffraction pattern to obtain the crystal structure back. So there are basically 4 broad categories of the techniques which are employed to measure the diffraction pattern of a crystal, and those I will be discussing today. So one is due to Bragg. The Bragg himself actually devised some diffractometer, which was then used to determine the diffraction pattern of a crystal. Then Laue diffraction methods. Laue is, the diffraction methods which were designed by Laue. Then there is another diffraction technique which is based upon rotating crystal method, where crystal is rotated. So we will be looking at that also, that how a rotating crystal based techniques can be used to measure the diffraction pattern. And the last one which we will be talking is powder diffraction methods. So in these methods, what we do is we employ powdered sample for measuring the diffraction pattern from a crystal. What do we mean by powdered sample? Is that a crystal which is not a single crystal, and we have very small crystals in the form of a powder, and that powdered form of the crystals is used to measure the diffraction pattern. So the situation is similar to that of sodium chloride salt. I have also discussed earlier as well, that you can consider sodium chloride to be, the common salt at your homes, to be made up of those small crystals of sodium chloride. So that kind of powder, when employed for diffraction technique, is termed as powder diffraction method. Now, there is one very common question which people ask in vivas or interviews, and that is the question is that why we actually measure this 2 theta. So if you see, usually a graph showing X-ray diffraction pattern of any substance, actually on x-axis shows 2 theta, and on y-axis it shows the intensity of the diffracted X-ray beam. So one very common question is why we actually put up 2 theta, why not theta versus intensity? So yes, anyone from you, have you ever thought of this? Why we actually measure 2 theta versus intensity and not theta versus intensity? This is a very basic, simple, common sense based question. So why don't we measure theta?
So because the diffraction patterns can be seen both upside and downside as well.
Upside and downside.
And theta is the
okay, please continue.
The diffraction patterns are observed from the center, upside from the center and downside from the center.
Okay, anyone else? Sandeep or Rahul? Okay, fine, no problem. So here it is very, the idea is very simple. Let us go to that typical Bragg's notation of crystallographic planes. So let us assume we have some set of atomic planes, and on those planes, suppose we incident some X-ray beam at some angle, say theta. So what will happen? They will be, of course, diffracted at certain angle, depending on where we are getting the diffraction condition satisfied. That is n lambda equals 2d sine theta. And if we draw perpendicular to these planes, these atomic planes, then and this is what your theta is, then this angle is also theta. I hope we have discussed this in detail in our earlier lectures, so no need to go much into this. But yes, that's the geometry. And if we produce this path of the X-rays straight, then what you can say is that, okay, when you are performing X-ray diffraction experiment, you will be in a position, or you will be able to detect actually one undeviated beam of X-rays, which is actually directly along the path, along the incident path. So it's not that every portion of the incident beam is diffracted, but a big chunk of this input X-ray beam is actually observed as such without any kind of deviation. So this we can refer as the incident beam, right? And this somewhere, if you have a photographic plate, this can be observed as a central spot in any X-ray diffraction measurement. So now, if we see this angle, what will this angle be? This angle is going to be 90 degree minus theta, this angle, correct? Angle of incidence, you can say. So what is this angle? These are opposite angles, opposite or alternate angles. You check it. So this angle is also 90 degree minus theta, correct? Opposite angles, fine. So this is 90 degree minus theta. So what about this small angle here? This angle will also be theta, because this total is, this is perpendicular. So this angle, which this undeviated path, or the path of undeviated beam makes with the plane, atomic plane, will be theta. So what is this total angle? This total angle is going to be 2 theta, theta plus theta. So that is why we measure, we actually plot 2 theta versus intensity. Now you will say, oh, what is the, I mean, I showed certain angles, did a basic geometry, and then we saw that, okay, this is what is going to be 2 theta. But what is the experimental advantage of doing this? So experimentally, you have some central spot, which is coming from undeviated X-ray beam, and then you have some diffracted beam, right, observed at certain angle. Now, instead of doing some transformation and looking for what should be theta in this whole geometry, we don't bother about all those things. We simply take, okay, central spot and measure the angle between the central spot and the diffraction peak. So this angle, straightforward, directly gives us the value of 2 theta. So it doesn't make sense to increase unnecessary mathematical complexity and do those unnecessary calculations and then represent theta versus intensity. Rather, what we do is we measure 2 theta versus intensity. So that's a clear, straightforward response to this. I hope this makes things clear to you. Is this clear? I mean, could you convince yourself, or are you okay with this explanation? Or is there any further question on this part? Okay. Ankush, you have any doubt? Or it is okay?
No, no, sir.
All right, fine. So that's why, I mean, typical conventional question which people ask. So that is why I thought of incorporating this here. So now anybody, if they ask you, you should be in a position to answer. You have to draw this small, simple diagram, maybe on a paper, and then say that, okay, that's the convenience of doing so. Now we will be discussing different experimental methods to actually measure the X-ray diffraction pattern. And this setup is actually showing Bragg's X-ray spectrometer. So this spectrometer was designed by Bragg, and that's why known as Bragg spectrometer. This diagram has been taken from S.O. Pillai's book, so you can go for details there. So basically, this setup consists of some X-ray tube. So we won't be discussing in detail what is the detailed construction of X-ray diffraction or X-ray source or X-ray tube. So I mean, what is the job of this tube is actually to generate X-ray. So how does this tube work is that, okay, you incident some high energy electrons on some X-ray source. There is some material here, typically tungsten or some other material. There may be copper source, tungsten source, different types of sources. And then what does that do? That produces some characteristic X-rays. And what will be the wavelength of X-ray? That will be the characteristic of the source sitting in the X-ray tube. So that X-ray then is actually incident or passed through two slits. You are here in a you are seeing here two slits, S1 and S2. So basically, what these two slits are showing, one is showing a collimator. So what is the job of a collimator? So then X-ray tube may not be giving you a perfectly parallel beam of X-rays. So what is the job of the collimator is to chop off unnecessary X-rays and keep only those which are traveling parallel to the particular or which are traveling in a specific particular direction. And what is this second source is called monochromator. So why monochromator? Because whenever any source emits X-rays, those X-rays are not exactly monochromatic. So there always is a there always is some finite width of those wavelengths around central peak. So whereas for performing X-ray diffraction experiment, the wavelength of X-rays must be fixed because it is n lambda equals 2d sine theta. So if you have different wavelengths, what will happen? In case, okay, let me ask it from you. Suppose we have a X-ray source which is not exactly monochromatic. I mean, there is not one single wavelength, but it has closely spaced small wavelengths. So what will be the effect of that non-chromatic beam on X-ray diffraction pattern? Let us say, okay, the broadening is not too large. Broadening in wavelength is not very large. You have wavelengths in a close region, but of course not exactly monochromatic. So what will be the effect of that on X-ray diffraction pattern? Yes. You can type your answers. I am following the chat box as well, or you can unmute your mic and speak out. Am I audible there? Okay, broadening of the pattern. Sandeep is saying broadening of the pattern, correct. What else? Anyone else? Peaks at several points will be observed. Okay. So basically, what Sandeep is saying is something relevant and okay. Sahil is also saying, I mean, almost it is within common sense that peaks at different points will be observed, because if you take lambda 1, lambda 2, lambda 3 different wavelengths, what will happen? That you know theta n lambda is equal to 2d sine theta. So that if I want to find out theta will be n lambda, the central peak, or the peak with or the intensity with highest, I would say the X-ray with highest intensity. Then in that case, there will be highest intensity in the diffracted pattern corresponding to lambda naught, and there will be some peaks nearby other X-rays nearby to the lambda naught wavelength. So because of this, what will happen? There will be some broadening of the peaks, but the X-ray. So broadening of the peaks can be because of many other factors, like size of the crystals. If crystals are of a very small size, like when you go to the X-ray diffraction pattern of nano crystallines samples, then you see peaks gets broadened. So there are not many other factors, but yes, X-ray non-chromatic nature of X-rays is also one possible parameter which can be seen for broadening. So, I mean, to get rid of all these uncertainties, what we do is we employ a monochromator. And what does monochromator do? It filters out all the wavelengths and only keep one specific wavelength. Then you may have a quick question here in your mind, how this monochromator must be working. So interestingly, monochromator is also a single crystal, which employs Bragg's law of X-ray diffraction to filter out all other wavelengths. How this works? So you take a crystal, right, place it in a specific manner so that your incident beam is coming on certain specific set of atomic planes. And what will happen? That that set of planes will specify diffraction condition for various wavelengths at various angles. So what we do is we arrange our setup in such a way that the peak which corresponds to the highest intensity is taken out for the measurement further. So in your output wavelength, you have only that specific peak at that specific angle which we desire to use. So the monochromatic meter itself employs the Bragg's law of X-ray diffraction. And then once you have a monochromatic beam of X-rays, then here is your sample that is incident on the sample. Then, okay, I mean, you may have some photographic plate so in this case, actually, Bragg setup, we don't have a photographic plate, but we use an ionization chamber to detect the diffraction pattern. So basically, this is undeviated beam. You may notice, you may measure where is the undeviated beam measured as such, the central spot, you can say. And then here, we measure it at different angles. I mean, where is the Bragg setup? This means. And then what happens is, so there is a peak in X-rays at whenever diffraction condition is satisfied, and then we employ here an ionization chamber. I hope you have done it somewhere in your BSc class. So what happens there is when we incident the radiation in the ionization chamber, so it is filled with some chemical compound. Something typically say this methyl bromide. And what happens when X-ray falls on this in this chamber on these vapors of this compound? So this is ionized by the X-rays. So you will have CH3 plus ions and bromine negative ions, and because of this, what will happen? The conductivity. So here is some high voltage applied across the chambers. These are electrodes, cathode and anode. And then what happens is that there will be some increase in current accordingly. So whenever there is a high intensity X-rays, there will be high conductivity, and accordingly you will notice a high current here in the ammeter. So this is something like an ammeter is employed. So that is how we can measure the intensity of scattered X-rays with the help of this ionization chamber. So this whole setup is designed by Bragg's, and that is how it is called Bragg's X-ray spectrometer, and that is how we can measure 2 theta versus intensity. And then from that data of 2 theta versus intensity, we can get the information of crystal structure back. So how do we get the information back? So we have discussed in previous class that we can theoretically calculate the X-ray diffraction pattern by assuming that, okay, what if this is the crystal structure, then we can compute the X-ray diffraction corresponding to that structure, and then we try to match that theoretical pattern with the experimental one. And then if that matches, means we know what we assumed, that okay, this is the particular structure for this crystal is correct. Otherwise we will go with the different model. So that's not that simple, and also it's not that hit and trial kind of thing that you have to begin with one model or the other. So there are certain standard set of softwares which helps us get rid of certain possibilities, and then certain hints we can get out of that. So getting or determining crystal structure completely is in itself a big field, and that comes under crystallography, and it's a detailed thing. So here we will just be understanding the basics of the techniques. Then of course, if you are interested in doing the detailed aspects of how we can actually take some unknown X-ray diffraction pattern, and then from that how we can get the exact information of the crystal structure, then that requires somewhat more detailed techniques. So we won't be doing that here. But yes, there are many softwares, and there is one popular method called refinement, where we do refinement, or we do fit our data to certain experimental pattern, and then we do take experimental data and fit it to certain model, and then try to match things, and that is how we fix up the things and obtain the information related to the crystal structure. Well, so that's one method. Then second method is rotating crystal technique. So basically, rotating crystal technique. In rotating crystal technique, what we have is we have some chamber in which we have some pinhole for input monochromatic X-rays. Now, how we get monochromatic X-rays is already discussed in the previous slide, so we don't need to talk about this again. So this is how X-rays come from this end, and then these are the X-rays which are undeviated ones. So we can measure the central spot from this. And then there is some photographic film here. You have a crystal mounted here in the center, and this crystal is also kept on rotating. So this is a different setup, right? Here, this is fixed. The the photographic film is fixed, and then the crystal is kept on rotating, and we measure the diffracted beam with the help of crystallographic film. And then that is how we can observe the diffraction pattern at various angles observed from the crystal. And then depending upon at what angle is what peak, we can again get the plots for 2 theta versus intensity, and then the same thing can be employed to study the theoretical model or crystal structure of the given material or given crystal. Main thing here is that you should know what is the geometry and how we measure the beam, and where is that rotating crystal mounted and all that. These are basic setups which you need to understand. And of course, when you go to certain lab, then you have to deal with a lot of controls related to that particular setup. So that is something, advanced level of things. So we don't need to get into that, because that will be possible when we have a particular proper lab demonstration for this. But anyway, at least whenever you go to certain lab, you should be in a position to identify what thing is what, and how the things are being done in a particular instrument. Well, then there is another experimental technique, which was because of Laue pattern, Laue diffraction method. So basically, in Laue diffraction method, again we have X-ray incident X-ray beams, and then we have a crystal mounted here. And then what happens here is that okay, you have a collimator here. There will be a monochromator as well somewhere. White X-ray beam means, it doesn't mean that it looks white, but it means that we have non-monochromatic beam. The analogy lies in the light. White light means it contains all the wavelengths. So similarly, sometimes it is referred as, a non-monochromatic beam is called white X-ray beam. Then you have a collimator, then monochromator, then that is incident on crystal. Then you have a undeviated beam. So this method is usually employed for thin films, because okay, what it measures is one set of X-ray beam is transmitted. So there is a transmitted diffracted pattern, and then one diffraction pattern will be observed because of reflection. So I don't know if you have done it. You should have done it in your BSc, diffraction through thin films. So diffraction through thin diffraction through thin films here. Then there you have one transmitted beam, one is reflected beam. So both the beams are related to the characteristics of the film or thickness of the film. So basically here atomic planes can be seen as made up of very small thin films, closely spaced, I mean very small, closely spaced thin films, and those are the films which produces the diffraction pattern. So here we measure the transmitted pattern. This also gives you the information. So you see here spots, and those spots are called Laue spots. And what does those spots reveal? Those spots actually reveal us the information related to the uh, uh, information of the lattice and basis. Of course, the intensity of the spots related to the basis, and then location of the spot is related to the lattice corresponding to that particular crystal. But one very, I mean, what you can call delimitation, you can say, of this method is that it requires crystals of specifically larger size, or even if you are employing thin films, then they should be of reasonably larger size. Small size samples can't be used in this method. And then at the same time, we also can measure the information coming from the reflected pattern in the Laue's method. So this Laue's pattern reveals the symmetry of the crystal, as I already told you, in the orientation employed. Orientation, I mean, okay, the crystal actually is mounted on this goniometer in a specific manner. So if the crystal is mounted in such a way that, I mean, that suppose 100 direction axis is parallel to the incident beam, then this Laue pattern will actually exhibit fourfold symmetry. Why so? Because X-rays now are being incident on the crystal parallel to 100 axis. So accordingly, the diffraction pattern, so it is something, I mean, why you would see the fourfold symmetry? This is actually related to the relation between real space lattice and reciprocal space lattice, isn't it? So if you have a 2D square lattice, for example, let us assume we have a 2D square lattice. So how will be the reciprocal lattice of this? That is going on. That is also going to be 2D square lattice. There's a reciprocal lattice for 2D square lattice in real space is also 2D square lattice, and each point in the reciprocal lattice is representing what? One Bragg's peak, isn't it? Because I hope you, if you go back to the that analysis of reciprocal space, then we had done something called evolved construction, right? So evolved construction means each point in the reciprocal space which is lying on evolved sphere refers to the particular diffraction peak, right? So indeed, each point of the reciprocal space has a information related to X-ray, the diffraction peak. So similarly, I mean, how will the points on this screen be observed? So they will be observed according to what is the symmetry of the crystal and how it is mounted in reference to the incident X-ray beam. So basically, this photographic plate is giving us 2D information, not a 3D information. If you employ a full sphere actually around the crystal, full spherical observation, I mean photographic plates, then you can see the full 3D pattern of the diffraction, the diffraction pattern. So we can see full 3D diffraction pattern, but here we are employing 2D imaging films. So that is why we will be able to see information with respect to specific plane, set of planes. So we are saying, okay, the axis is mounted in such a way that the 100 direction is parallel to the incident beam, then we will be seeing Laue pattern on this photographic plate accordingly. Fine. So this is, I mean, that's all the setup of this Laue diffraction method. So you may be asked, okay, what is the basic setup for Laue diffraction method? So that's what the whole setup is. So there is nothing, I mean, very unknown here. So any method actually, basically they are employing different way to observe diffraction pattern. So all the things will be one or the other way arranged in here or there, but the basic thing has to be common. I mean, you have to have some monochromator, there has to be some X-ray beam, there has to be some measurement or measurement screens which can measure the intensity of the X-rays. There has to be a crystal mounter or sample holder, something like this. So this all is common in all these techniques. Then there is another very important technique, which is actually powder diffraction method. So this powder diffraction method is again the same technique which is used to measure the experimental X-ray diffraction pattern of any crystalline sample. So basically here, the sample which we employ is powdered sample, and this is one of the largely employed technique to measure X-ray diffraction pattern of any crystalline material, because usually we don't have single crystals. Most of the times we work with the polycrystal subsamples, because single crystals are not so easy to grow. So whenever you are synthesizing some crystal, practically you get small size crystals, and they are usually in the powdered form. And then to get single crystal, there is additional step. Then you have to follow the techniques of growing single crystals. But okay, to understand the properties of the crystal, even polycrystalline samples are okay. So most of the groups actually works with the polycrystalline samples only, and that is why this technique is very important. I mean, this is employed at many places to study the X-ray diffraction pattern. So basically here again we have some X-ray tube, then those X-ray sources are incident onto the sample. So here is your sample mounted. So you have a collimator, some monochromator. Here is your sample. Now you can see here this is 2 theta. So this is the photographic film, something like arranged in some cylindrical pattern. So you have sample, and then around this you have a photographic film. So this photographic film is also, I think, some kind of textbook thing nowadays, because most of the modern instruments do employ semiconductor detectors, which can actually detect X-rays, X-rays in the form of some current, and then that is directly stored in the digital form, or we can directly measure the values. So this is 2 theta. So the angle between incident beam and the diffracted beam directly is 2 theta. So that's how it is measured. So typically what we do is we take a film, we take these photographic films and film after X-ray is over, because now since the sample is in powdered form, so you have different crystallographic planes available at once, because in powder form you are not orienting the planes at your choice, so they are randomly placed. I mean, the atomic crystallites are randomly grown in different directions, and then we are placing those powdered grains in a random fashion. So because of this, the moment you incident the X-rays here, so what you can call the whole pattern is generated at once. So you have peaks appearing at various angles just the moment you shine the X-rays here. Then you can measure this, and then you will be finding, or by looking at this photographic film, if you straighten this, so this film, now suppose we straighten it, so we will be seeing a central spot which is coming here at point, say, O, and then you will be observing the peaks like this here. So these various lines are representing X-rays because of various diffraction peaks observed at different angles. So why these circular kind of things are there? So I hope you remember that Laue interpretation or Laue equation. So what we will be observing here is because of powder diffraction. So this is not at this specific angle, but we should be actually observing a full circular kind of pattern, cone. So I mean, there will be a peak along the surface of the cone. So that if I draw a plane here, so there will be actually a circle on that plane. So you should see a full circular kind of pattern, but since we are not employing a very large size photographic plate, so you should be seeing this kind of curved peaks. And exactly at 90 degrees, so this is representing 90-degree spots. So when we are at 90 degree, so the circle is going to be bigger one and perpendicular to this plane. And that is why these peaks are vertical or totally straight. Why straight? Because the circle in this photographic plate will be perpendicular to this circle. So these two circles, I mean, this is the circular arrangement of the photographic plate, and then there is a circle again perpendicular to this, and the center of the two is exactly the same. So that is why these peaks are going to be straight. Why I am bringing your attention to these peaks, because okay, they act like a reference. So those straight lines actually refers to the 90-degree situation. So that is how we can employ, even the powdered samples for measuring the X-ray diffraction pattern of any crystalline material. Now, before I move to the next slide, I would like to ask you if everything is clear, or is there any doubt or question from your end on this part, or on whatever we discussed till now. Sandeep is asking, oh, I am not audible. I'm sorry. I just saw the message from Sandeep. Is it better anyhow now? Am I audible? Okay. Sandeep is asking, intensity of diffracted beam depends upon number density. Yes, of course. Number density of electrons. Can we find out composition of basis from that? Yes, exactly, Sandeep. We can find out here, just now, that Ritwell refinement technique. So there what we do is, we start with the model, and in our model we have lattice, we choose a space group, and then we also choose the basis of atoms, where atoms are placed at specific positions, which we call the Wyckoff positions. So then what we do is, okay, let me give you a quick overview of how we do Ritwell refinement. We take X-ray diffraction data, 2 theta versus intensity, and then in the software we choose some space group. So okay, we have some reference usually whenever I'm synthesizing a sample and then doing some sort of doping or something like this. So we have a lot of there is a big database from which we can try to guess, okay, where all we are getting the peaks and what is the possible crystal structure we are getting. So from that we pick up the space group, and then we also put in the atomic positions there in that software, and then those are all tentative. I mean, we decide some tentative lattice parameters, then some tentative atomic positions. But of course, we know the stoichiometric ratio or the formula which crystal we have synthesized. Because whenever we mix certain reactant chemicals to create a crystal, then we already decide that, okay, what is the stoichiometric ratio of those elements according to which we are expecting our crystal to get formed. So then we put all those values in the software, and then we generate a rough X-ray diffraction pattern, the calculated one. And then software compares the both. Then sometimes we get totally different pattern than the experimental one. And sometimes what we may get is that, okay, certain peaks are shifted with respect to experimental one, certain theoretical peaks are shifted. In certain cases, they are shifted, suppose, to the right. In some peaks, maybe shifted to the left. So all that things then are fixed in the model. Suppose we have a theoretical generated pattern and one experimental pattern, and there are two peaks. I mean, one peak is shifted to the right in theoretical pattern. Suppose there is one peak which is shifted to the right. Let us assume that peak is say 001. Suppose there is a 001 peak and that is shifted in theoretical pattern to the right. So what does this mean? If you employ n lambda equals 2d sine theta, then theta is higher in the theoretical calculated value. This means d should be what? D should be lower, right? So means in our model, we have chosen the lattice parameter, which may be referring to C axis, because 001 peak we are talking. So which may be referring to C axis. So actually the length which we have taken for the C axis is smaller, because D is smaller. That is why theta is observed or calculated at higher angle. So then our model fixes that value of C in such a way that the two peaks match with each other. And then that is how this kind of matching is done by the software. And then finally there are a lot of things again. I mean, even suppose atomic positions are tentative,
we didn't know what were the atomic exact atomic positions. We fixed them. Then our X-ray peaks may not match. So then we also try to move the atomic positions with the help of that software in such a way that the atoms or the atomic positions which best reproduce the experimental pattern are considered to be better one. So that is how a lot of hit and trial, how a lot of smart guesswork goes in obtaining the or fitting the this retooled refinement pattern for any X-ray data. But yes, I mean, what Sandeep had asked, yes, can we obtain the information for basis? Obviously. I mean, what all atoms are constituting our crystal and at what positions those atoms are sitting, that all can be obtained by fitting the data with the help of those softwares. That is okay. Yes, any other question, please? Any other question, if there is? No from Harish. Others? Rahul? Okay, fine. Well, so I mean, these were four broadly classified diffraction techniques. Now we may ask one question: are X-rays mandatory for understanding crystal structure? So let me ask you. I mean, is it mandatory to take only X-rays? What do you think? Or what can be the alternates for the X-rays? Okay, can you name some alternatives for X-rays? Can we study crystal structure without employing even X-rays, or without employing X-ray or some other source we can employ? So obviously we can't employ visible light because the wavelength of visible light is what? Is it very large or very small in comparison to interatomic spacing? This is also a very common Viva question. Why can't we employ visible light to study X-ray diffraction pattern? This is because the wavelength of the visible light is very, very large in comparison to the interatomic spacing. Whereas to observe the X-ray diffraction pattern or any diffraction pattern, the wavelength of the radiation should be close, comparable to the interatomic spacing, right? So it's somewhat because yeah, correct. Ankit said most of you are getting it correct. Fine. So this means okay, visible light is not possible. Then what other thing? So if we focus on electromagnetic pattern, then the region or the portion of electromagnetic pattern which is best suited for studying the crystals is X-ray only. So from electromagnetic pattern, X-ray is the best suited component. But then we may choose something other than those electromagnetic patterns. So there can be something like electron diffraction. Well, do you think electrons can produce diffraction pattern? Have you heard of this term called electron diffraction? Neutron diffraction is okay. Dharmendra is saying fine. Can electrons produce diffraction? What do you think? Very good. Electrons can produce diffraction. I hope you would have heard of this very popular and very famous experiment by Davison and Germer. So basically what Davison and Germer had done, they had employed electron beam to study diffraction pattern from a nickel crystal, I think. And that is really something interesting. And this experiment was a very landmark kind of experiment also, because yes, we do it in quantum mechanics, because this experiment established a very interesting fact. And the interesting fact was that electrons, which earlier were supposed to be particles, because J.J. Thomson, when he had invented electron, he had characterized its certain properties, and he found that it behaves like a particle. That was a very well established fact, almost like 100 years. But then there were this experiment, I mean, by Davison and Germer, actually experimentally proved that electrons can also behave as particles. So what idea they had employed? They had employed the idea of this wave particle duality associated with all the subatomic particles or quantum mechanical particles. So electrons, even if let us assume they are particle, they also have a wave character, and then that wave character has because of that wave character, electron beam also has some wavelength associated with it. And now if this wavelength actually happens to be of the order of wavelength of X-rays or wavelength required to study the diffraction pattern from the crystal, then obviously we should observe a diffraction pattern. And this Davison Germer actually had obtained the diffraction pattern, and that is what was a great verification of the fact that electrons indeed have dual character, and they have wave character as well as particle character. And well, then what is the advantage associated with the electron diffraction? That we can tune the velocity of the electrons. If we accelerate them with the help of some potential, say u, then the velocity associated with the electron can be obtained. So this is just half mv square is equal to energy E into V, right? So that is from where we can find out the velocity. So the velocity of the electrons is known to us, means you can, by varying the potential or accelerating potential for the electron beam, we can tune the velocity of the electrons. And once we can tune the velocity of the electrons, we can tune the wavelength of the electron, isn't it? So once we have the electrons of a desired wavelength, I mean the one desired for study of diffraction pattern from the crystal, we can employ that beam of electrons to study the pattern of the diffraction observed from the crystal. And in transmission electron microscope, this diffraction technique is employed very much. And the wavelength of the electrons accelerated in TEM is much smaller than that of radiation usually used. Also, I mean, what is important thing here is that we can tune the wavelength of the electron. That's the main thing which is there. So X-rays have a, I mean, we can't tune X-rays. Well, so X-rays lies in a specific region of the electromagnetic spectrum, and that's it. So here we can even employ electron beam of very smaller wavelength. So smaller is the wavelength, better will be the accuracy, isn't it? So smaller is the wavelength, better will be the accuracy. And because of this, we can get better information. I hope you have studied that evolved sphere, evolved construction. So evolved construction is then employed. I won't be talking much about evolved construction because we have already seen that there. So basically, if you have smaller wavelength electron beam, if we have a smaller wavelength electron beam, then because of that we can get evolved sphere of much larger radius, and that gives us far more better information regarding the reciprocal lattice. So I mean, more what we were discussing in context of that Lowey pattern, right? So you have a crystal mounted in specific orientation. Then when you take electron beam of a very small wavelength, then that can be employed to resolve the 2D pattern of the reciprocal lattice in more better fashion. Then you rotate crystal by certain angle, then you get further information in certain other 2D plane. So if you have to map a three-dimensional crystal structure or 3D structure, then you can imagine that to be made up of small slices made up of 2D planes, and that is how you can have far more better information of the crystal structure by employing electron diffraction pattern. Then what other things? Of course, neutron diffraction pattern. So there can be something like elastic neutron scattering, where I mean there is no loss of energy of the neutrons. And then there can be another very interesting technique called inelastic neutron scattering. I will be quickly talking about that after this. So, but okay, I mean, elastic neutron scattering implies the same thing. It is similar to X-rays. Neutron also, those are subatomic particles, and of course they have wavelength associated with them. Yeah, the great thing about the neutron diffraction pattern is that X-rays are good for surface level studies, superficial studies, uh, and they can penetrate only shallow depths within the specimen. So they are surface sensitive. I mean, they tells you the information of the surface or the atomic planes sitting onto the surface of the crystal. I mean, it is something like 10 to the power 4 to 10 to the power 5 atomic planes are penetrated by the X-rays, whereas neutrons have a higher penetration depth and hence can actually get the information of the atomic distribution or atomic planes in much deeper atomic planes from the surface. That's the same thing. I mean, neutrons we can employ in this fashion, and you can employ actually the neutrons of desired wavelength. So how to get neutrons of desired wavelength? That depends on, I mean, what is the source of the neutrons, and accordingly you can choose what source you want to employ, and then how we can actually get the neutrons of the desired thing. So that's not, I mean, detailed um, way to obtain a particular neutron beam is not part of condensed matter physics as such. But yes, we ask our nuclear physics friends to help us get a neutron beam of some specific wavelength, and then we employ that. Another very important aspect associated with the neutron diffraction pattern is the magnetic character. So the neutrons actually are also containing some magnetic moment, and those magnetic moments of the neutrons can actually interact with the magnetic uh, I mean, you can say the magnetic atoms if they are present in the crystal. So by employing the neutron diffraction practically mainly is employed for studying the magnetism. So you can tell about how the atomic spins in a magnetic crystal are aligned by taking the neutron diffraction pattern. So if the crystal is non-magnetic, and then you employ neutrons and X-rays of exactly same wavelength, suppose, then the X-ray and neutron diffraction pattern will be exactly the same, because there is no magnetic element, though there is no magnetism, hence both patterns will match. But in case there is some magnetic moment, suppose your crystal is antiferromagnetic, then there will be additional peaks in neutron diffraction pattern, because there will be certain planes which will be atomic planes. So there is an atomic periodicity, and then there will be periodicity of atomic spins as well. I mean, magnetic spins. So in antiferromagnetic crystal, what do you have? Typical antiferromagnetic crystal, you may have one atom with the upspin, then neighboring atom with the downspin, then third atom with upspin further, and fourth atom with the downspin, and so on. So you have upspin planes which are now having interplanar spacing double the interatomic spacing. Means in a typical simple antiferromagnetic arrangement, you will have you can say the magnetic planes which has the interplanar spacing double the interatomic spacing. So you will be seeing additional peaks because of those planes. So if we are getting something like this, then we can do some kind of ritual refinement on the neutron diffraction data, and then can obtain the magnetic information as well. Well, I mean, then there is something called, this is elastic neutron scattering. Then we may have something called inelastic neutron scattering. So in elastic neutron scattering, the energy of the incident beam and energy of the diffracted beam is exactly same. There is no loss of energy. It is only the change in direction of the beam. But in inelastic neutron scattering, basically we employ certain neutron beam, and then that neutron beam may lose energy to the atomic lattice in the form of atomic vibrations. So that energy is also measured, change in energy is also measured, and because of this we can also obtain the information on atomic vibrations in the crystal. I mean, if you have to study the phonon spectrum of the crystal, for that also neutron diffraction can be employed, and specifically we have to look for a change in energy of neutron diffraction pattern and then that change in energy can give us the information about how the atoms in the crystal can take energy in the form of atomic vibrations. So that is also a very important aspect of neutron diffraction pattern. Oh, I'm sorry, I didn't ask you for signing your attendance. Please sign your attendance quickly in the chat box. Meanwhile, you can also ask me for any question if you have related to this. So this completes the experimental techniques which can be used for study of diffraction pattern of a crystal and how we can determine crystal structure of any crystalline substance. Yes, any questions, please?
Sir, if we consider atomic vibrations in the crystal due to heat, then what will be the effect of that vibration on the diffraction pattern?
Diffraction pattern, so there are two things. I mean, you're talking of X-ray diffraction pattern?
X-ray diffraction.
X-ray diffraction pattern. So there is something called area of cross section. So if you are, area of cross section of each atom, right?
Yes,
so
sir.
If you are saying, okay, my atoms are exhibiting atomic vibrations, so what will happen? That effective area of cross section will increase.
Yes,
right?
Sir.
Because atoms
Yes,
are now vibrating and they
yes,
are not no longer localized at that specific position. So that area of cross section will be increasing, and that will affect the shape of the peaks in the X-rays. So there are certain shape parameters when we do Rietveld refinement. Of course, those are helpful in determining all those things. Mainly the shape of the peak will be affected because of that. Atoms won't be vibrating so rigorously that even the interplanar spacing will change. No, that is not going to happen. So practically, most of the times the peak shape parameters are affected. And that is what we can employ to, see, that peak shape of the peaks can be employed. But then that is important in case we are measuring, suppose, X-ray diffraction pattern of a crystal at a very low temperature, suppose something like a 10 Kelvin. Then if we take X-ray diffraction pattern of the crystal at something like, say, 400 Kelvin at high temperature, suppose, provided the crystal doesn't melt.
Yes, sir.
Then those two diffraction patterns will differ from each other, and then you will see that peak shape parameters, when we calculate from Rietveld refinement of these two extreme cases, will be different. However, whenever we are doing X-ray diffraction pattern at room temperature, so because everything is at a specific temperature, then usually we fix those parameters because we are not doing a temperature dependent X-ray. So in that case, we can fix that to be constant, and we don't want to bother about that.
Okay.
Is that okay, or
Yes,
is there
sir.
any further query?
Okay, sir.
Okay. Any other question from anyone? Yes, please. Well, so if there are no questions, that's all for today. Tomorrow we will begin with the next unit. I think our first unit is done now. So tomorrow we will start with our second unit. And